let's start where we are left off yesterday. So I wasn't being able to solve it because it was too late and I was sleepy, and I was just couldn't focus on. So this is a backtracking problem. So obviously this is the first question that I am doing after learning about backtracking. So let's see. I'm gonna give myself 30 more minutes in order to solve this problem, and if I can't do it this time, then I'm gonna check out the solution. You know what? I'm gonna give myself 20 minutes, which this one isn't correct. Given the root of a binary tree and an integer target sum, return true if the tree has a root to leaf path such that adding up all the values along the path equals the target sum. A leaf is node with no children. A leaf is a node with no children. Okay, basically this right here doesn't work because 5, 4, 9 plus 11, 20 plus 7, 27, but the sum is 22, so that doesn't work. Looking at this path, 5, 4, 11 equal to 20, 20 plus 2 equal to 22. Okay, this does work, right? So here, target sum equal to 5. We go this way, doesn't work. We go this way, doesn't work, so false. Okay. So I need to store the values of the node into a stack so I can add them up to see if it adds up to target sum, correct? So let's do that. And I don't know how I'm gonna implement it, but let's see. So define path root to leaf will be root, and then I don't know, should I say target sum? What am I passing into so that, yeah, we need to have target sum, and then we're having the stack, right? Having the stack. Alright, let's go. Okay. So if not root, then that means return false, right? Because we don't have anything here, then we just return that. And if there's no left node, there's no right node, we're gonna have to check if not root dot left and not root dot right, then we do return no. Then if there's none, we have to check if sum of stack is equal to targets some. Then we can do return true, right? Or else just return false. Return true or else return false. Okay. And else if we do root to leaf root that targets some stack that append. I mean, wait. So does that mean that I have to append here? Stack that append a root that fell? Right? Okay, and then return true if root to leaf root right target some stack return false and true as well. Forgot that. And right here we have to do, so if both of them doesn't work, we do a stack that pop. We just do stack that pop and false. And now let's call our function root that target some stack. Okay. Right. Oh no. Why is that? Why wouldn't it work? Or does it work like this? I don't know. Let's see. Popping from an empty list. Alright, so that's not the case. Alright, I think. No. This should go here. Maybe that's the mistake I'm making. I don't care. This needs to go. This needs to run. Alright? Okay, it's not running again. Why? Why wouldn't this work? Why wouldn't it work? Why wouldn't it work? Why wouldn't it work? Why wouldn't it work? Stack equal to, okay, we passing in the root and then target leaf. If there's no root, then we just return false because, you know, yeah, why not? And if it has a value, then we just append it into root that value. Then we check if there's a left side or if there's left side. If there's none, then we check now. That means we came to the leaf node and we check the sum of the stack. Is it equal to target sum? Right? If it is, then we return true. If it's not, then false. Then we go back. And then if this doesn't get executed, if we have left node, we check if the root to root leaf, we check left with target sum with a stack, and I don't see why this wouldn't work. Honestly, that's all I can think of. I think we're gonna check it out. I think we're gonna check out the solution. Give me a second. Give me a second. Let me pull it out. Alright, let's check out his explanation. Let me stream this also so you can see it as well.
Problem path sum. We are given the root of a binary tree and an integer, which is our target sum value, and we want to return true if there exists a root to leaf path. A root to leaf path is basically a path that starts at the root node of the tree and keeps going down until we reach a leaf node of the tree. And a leaf node is basically a tree or a node that does not have any children. So it doesn't have a left child and it does not have a right child. Now, this is a binary tree, but it's not a binary search tree, meaning that the order property is not valid, right? So this 8 node over here has a left child of 13. That left child is not less than 8, but it's still a left child because this is not a binary search tree, it's just a regular binary tree. So the fact that this is not a binary search tree means that we definitely have to go through every single node of the tree. We basically have to look at every possible root to leaf path in the entire tree and see if any of those paths ends up totaling the target sum value. So just to kind of emulate what we're going to be doing, we're going to start at the root, 5. So our sum so far is 5. We're going to go, let's just start at the left side. We could go right, but let's go left first because it's kind of natural. Then we get a 4. This is not a leaf node yet, so we keep going. Our total so far is 9. We're going to go left again. We are at 11. Now our total so far is 20. And by the way, our target is going to be 22. So this is still not a leaf node. Now we go left again. Now our total sum is 27. That's greater than 22. So this, even though we're at a leaf node now, this is not what we were looking for. So let's actually backtrack. Let's not choose this path. Let's not go to 7. Let's actually go to the other node, which will give us a total of 22, and that's exactly what we're looking for. So now we actually did find a single path that does equal the target sum, so we can definitely return true. All we were looking for was at least one path, so we can return true now. But if we didn't find the leaf node in this position, we would have to try the other positions as well, right? We would, instead of even going down the left subtree, we'd have to go down the right subtree. We'd have to check this path, which is one path to a leaf node, and then the second path would be this one to the other leaf node. Neither of these paths ends up giving us the target value. So just by kind of looking at what I did, if you are familiar with binary trees, you kind of know what I did was basically an in-order traversal, right? In-order traversal and in-order DFS, depth first search, right? And the easiest way to code this up is usually to do it recursively. So we can do exactly that. It's a very simple DFS problem. The only thing is we'll be have to maintaining our current sum value, right? We'll have to keep track of sum total and then continuously check if that total is equal to the target sum, but we'll only be checking that.
I just want to see something, right? I just want to see something, right?
when we actually reach one of the leaf node in our tree. And we can check that by making sure that none of these nodes have any children, right? No left child and no right child. So with that in mind, we have enough information to actually code this up. Now let's code it up. We're actually going to be creating a helper function. We're going to call it DFS, and we're going to define it inside of our outer function. The reason we're doing this is we actually need to pass in one more parameter that the outer function does not have, and that is our current sum, our current total that we have so far. And we're going to be passing in whatever node we're at, but we do not have to pass in the target sum because the target sum is never going to be changing. And within our inner function, we'll actually have access to this outer value anyway. So one thing we're going to do is start with the base case. We actually could be given an empty tree in this case, and based on...
So, is there any changes that I can make? So he's saying that I can delete this part, right? So, because this is not needed, this is not needed. Right. This is not needed. Right, I mean, same thing. I don't think it's gonna run. Why is it always giving me the... Why is that?
one of the example cases that they gave us, if we ever have...
Oh, what if I, look this way? Is it gonna make any difference? I'm just curious. Just curious. Oh. Am I like messing on some syntax issue? I'm just giving a shot at this point. Huh? What do you mean by that?
Have an empty tree, we have to return false anyway, even if the
No, that's not the issue here. That shouldn't be an issue. Oh. If not node, know that value. Right. Still wrong.
target sum was 0, we still have to return false because there technically does not exist any root to leaf paths. But if the node is not null, then we can take the value from that node and add it to our current sum that we're keeping track of, and that's pretty easy to do. And
isn't that what I did also? Isn't that what I did? Alright, right here, I did that. Right.
the first thing we should check is now, intuitively, maybe we found the result, but how do we know if we did? Well, we have to make sure that this node is a leaf node. So basically, if not node.left and not node.right, so basically it doesn't have any children. And the last thing we're checking is, does the current sum equal the target sum? But we actually don't have to check this in a condition because we can actually do it just like this. If this is a leaf node, then we know we can't really run DFS on it anymore anyway. So we're going to return if the current sum is equal to the target.
That's what I did.
If it is equal, then we're going to be returning true. If it's not equal, we're going to be returning false. So it works out. But if that's not the case, if it's not a leaf node, then we are going to be running DFS on the left and right side. So let's say a DFS on node.left, passing in the current sum as well. And let's call it also on the right subtree as well. But the thing is, if either of these ends up returning true, then we can return true, right? We're only looking for a single path. So the easiest way to actually code this up is just to say return the OR condition from the return values of both of these function calls. So we're going to either of it also on the right subtree as well. But the thing is, if either of these ends up returning true, then we can return true, right? We're only looking for a single path. So the easiest way to actually code this up is just to say return the OR condition from the return values of both of these function calls. So we're going to say take the return values of both of these, OR them together, right? If either of these is true, then we can end up returning true. And that's actually the entire function. Now all we have to do is just call it. Let's call our DFS passing in the root node. And what should we pass in as the current sum? Initially, we can just say it's 0, and then we can return the result of this function. Now let's just run it to make sure that it works.
Oh my god, I think I figured out what I did. So I didn't call it. Return. Okay, will that work? Will that work, please? So was that the only issue that I was having? What? Right, didn't work. Alright, well, what is it now? What?
And as you can see on the left, yes, it's the result of this function. As the current sum, initially we can just say it's 0, and then we can return the result of this function. Now let's just run it to make sure that it works. And as you can see on the left, yes, it does of this function. As the current sum, initially we can just say it's 0, and then we can
Something's not right. So the issue here is that it's always returning false. I'm assuming that maybe it's because of this one. Oh, it's not because of that. Right, then what's the issue? But I'm asked GPT. What's the issue with my solution? I'm doing something wrong, and I don't know what it is. so GPT doesn't. I feel like he's pretty confused as well. I mean, not GPT, Grok. Right, stack. This, why wouldn't it work? Why wouldn't it work? Why wouldn't it work? If some is false or true. Oh, I think yes. So if that root or false, if that. Oh, wow. Yeah. So the issue is returning false here. Oh my. Bro, I was so close. That was the issue that I was having. Damn. I mean, yeah, I guess it happens. Took me an hour to solve this problem. Just because, you know, I mean, I didn't really solve, I mean, I had a bug, so technically I didn't solve it, but I see the mistake. Right, see you guys later, okay? Gonna end the stream now. Gotta go eat.